Evening, everyone. So before I turn to my my carefully written notes for this introduction, just the usual announcements. Mobile phones, obviously you want to keep them on for taking photos and so on, but please keep them on silent. And in terms of fire drills, there's none scheduled for tonight. So if one goes, then it will be real, or at least someone will have really pulled the fire alarm. And therefore we should follow the staff out to Stories Gate, which is, if you go out the front door, turn left and left again. That's where the muster area is. And I'll just get my glass of water. So it's great to see such a full house tonight. Thanks all for coming, and welcome also to those tuning in at home. I'm Damian Grant, the current chair of SecEd. I work for ARUP, and so on behalf of both myself and the entire SecEd committee, welcome to the ICE for the 19th Mallet-Milne Lecture. The term as chair for the SecEd committee, many of you won't know, is a 2-year term. And we also have the Mallet-Milne Lecture, probably not coincidentally, every 2 years. So it's kind of a highlight, I guess, of the chair's calendar, or the chair's term in office, to be able to host this event this evening, the Mallet-Milne Lecture. And not only that, that sort of the fact that I knew I was going to be looking forward to doing this, but it took on special significance when Professor Calvi accepted our invitation early last year to give tonight's talk. So it's a real pleasure for me to be here introducing him. Before turning to Professor Calvi, though, I think it's probably fair to say that the quality of the earthquake engineering and engineering seismology communities in the UK, we sort of punch somewhat above our weight, given the relative lack of earthquakes here. And I think in large part that kind of traces its origin back to the two folks that we commemorate with the Mallet-Milne Lecture. So, of course, Robert Mallet was an Irishman who did a lot of work in Naples after the 1857 Great Neapolitan earthquakes, and not too far away from where Professor Calvi joins us from today. And John Milne spent a lot of time out in Japan and developed the world's first seismograph network. Won't go into any more history of that tonight, but one of our previous Mallet-Milne speakers, Roger Musson, wrote the kind of definitive text, I guess, on the history of British seismology as his 14th Mallet-Milne Lecture. And his was also the first one, I think, that we managed to make open access. So you can go and look on the SecEd website and read that. I thoroughly recommend it. I think looking through the 18 previous the names of the 18 previous Mallet-Milne Lectures, one is struck by the quality, the consistent quality that we've managed to attract, or to invite and to accept our invitation to deliver this talk. And if I were to sort of pick out highlights, that would sort of make the people I don't pick out feel aggrieved. So all I'll say is that as a patriotic New Zealander, great to see sort of Tom Paulet and Nigel Priestley, two of our legends from New Zealand, amongst that group, people who Michele knows very well, or knew very well. Turning to tonight, though, it's great to be able to add Professor Gian Michele Calvi's name to that list of esteemed Mallet-Milne lecturers. Professor Calvi is a professor at the University Institute of Superior Studies in Pavia in northern Italy. And he's the current president-elect of the International Association of Earthquake Engineering. He's had a pretty phenomenal career, both in engineering consultancy and in academia and research. I think examples of the former are the Rion-Anti-Rion bridge that we actually heard about in the last Mallet-Milne Lecture 2 years ago from Professor Pavia, who worked on that project as well. And also the reconstruction in L'Aquila that we'll hear a bit more about tonight. Examples of the research are spread across his 250 plus publications, and the books that many of us have on our bookshelves, the sort of definitive book on seismic design of bridges, and the newer text, actually in the second edition, on direct displacement-based design. Both of those books co-authored with the 9th Mallet-Milne lecturer, Professor Nigel Priestley, who I mentioned before. In around 2003, Michele founded the U Center Foundation, which is a research institution also based in Pavia in Italy. But going back a few years before the foundation of the U Center, I first heard Professor Calvi's name at the end of the year 2000 when I was finishing my undergraduate studies in New Zealand. And I heard of this new master's program about to start on almost literally the opposite side of the world in about 2 months after my graduation. So 2 months later, in January 2001, I was studying in Pavia, in this town I've mentioned a few times, and with 5 other students, so a very small class. And I think at the time, we didn't really appreciate what a significant kind of school this was and what a quality and a innovation of education that we were getting from that program. I think Professor Calvi's great innovation there was to bring a number of international luminaries, much like the kind of people we have on our Mallet-Milne list, to give short courses in Pavia, but short, intense courses, condensing kind of a semester's worth of work from their own university into a 4-week period, but to offer those courses in series. And so we were getting lecturers from Europe, from also the UK, Japan, New Zealand, the United States, all as part of our master's program. And it's interesting actually to see that of that first years of the Rose School, 2001, Michele is the 3rd of the lecturers who taught us in that first year. And then Alain Pecker, as I say, the last Mallet-Milne lecturer, I think taught in 2002 or 2003 for the first time. So 4 of our Mallet-Milne lecturers have been on that teaching staff in the early days of the Rose School. Professor Calvi's lecture tonight, as you can see on the screen, is entitled Risk Management and Rehousing of People Displaced by Earthquake Disasters. And I think, like many of the best Mallet-Milne lecturers or lectures, this really brings together a lot of different threads of Michele's work over the years, from seismic design, disaster management, base isolation design, construction management, and so on, as you'll see tonight. Once again, I mentioned open access before. Once again, tonight's the lecture, the written publication accompanying the lecture is available in open access. And unfortunately, that's quite expensive. So two things to say about that. One, please, all of you download and read it so we get our money's worth for making that open access. And secondly, that kind of brings me to talk about the sponsors. So thankfully, we've been able to offset a lot of that cost with the support of the sponsors for tonight. So gold sponsors Ramboll and Servotest. Thanks very much to them. And silver sponsors Jacobs, AWE, and Atkins Realis. Many thanks to them, and many of them are circulating this evening. Before handing over to Professor Calvi, thanks to Jared O'Reilly, can't see where you've got to, who did a lot of work helping review the manuscript for tonight, as did Fabio Freddi and Mark Scorer from the SECA committee. Thanks to the rest of the SECA committee for helping with the organization. And also thanks to ICE staff. We had Kath and Elira helping out on the desk tonight. Shelly Ann, who wasn't available tonight, also did a lot of work behind the scenes to get this up and running. Program is pretty simple, so I'm just about done, at which point I'll invite Professor Calvi up to deliver the lecture. After that, we'll have a vote of thanks from Dr. Christian Mulliger from Imperial College of London. And then I'll return here to briefly wrap things up and lead us all into the Rennie room. That's me done. So now just the only thing to do is to welcome Professor Gian-Michele Calvi to the stage to deliver the 19th Mallet-Milne Lecture. Thank you.
Thank you, Damian, for your presentation. That reminded me a lot of nice moments of my life. As you have realized from Damian's introduction, I'm a rather old person now. So in the process of leaving an heritage more than putting seeds. But Damian's introduction made me somehow remembering that there is one constant point in my life. I've always believed that the real treasure is people. And actually, when at the end of the 90s, I somehow invented the format of the Row School, and then I discussed it with my best friends, Nigel Priestley, and he created it. The first idea that where it came from was the fact that I had been a student in Berkeley another almost 20 years earlier. And at that time, my professor at Berkeley were Joe Penzian, Vitelmo Bertero, Alex Cordelis, Ed Wilson, Graham Powell. Well, you can imagine. So it was the Berkeley of the giants. And I was thinking, how can I try to reproduce something like that? And the answer was easy. The answer was it's impossible, because it's impossible for any university today to put together a team like that. And that's why I came out with the idea of having short courses one after the other, and to ask all the friends around the world, from Japan, from New Zealand, and so on, to come for a month and to teach a 60, 70 hours course. And then there was again a dream team there. And as you are remembering, some of them have been Mallet-Milne lecturers, but not only that, it's the measure of the value of an award is the list of the recipes of the award in the past. And this is what makes you proud of it. And you start with the Nick Ambrases, and then you have George Hausner. It's enough. But then you see that there is Tom Poley, there is Nigel Priestley, so on and so forth, and it's more than enough. So it's a great honor to be here. It's a great honor because of this past, but not only because of this past. When I entered this building tonight, lots of memories. I'm sorry I'm spending part of my time in these things, but I think it's not wasting, actually. And, each one of us, we're all engineers. We have been reading many books. And the role of UK engineers in the 19th century has been so fundamental in the development of so many practical issues. French engineers were developing theories. British engineers were constructing railways and bridges. I'm not saying that the theory is nothing. It's very important. But if you think in these terms, you understand why this building is here, is next to St. James Park and Buckingham Palace and so on. I mean, it's because there has been a real fundamental and crucial role in the growth of this country due to civil engineers. Now, let me come to my lecture, otherwise I'll finish too late. And when I was asked to give this lecture, I decided that I should have been developing something that was new to me at least. I had just, at that time, I was publishing a new book that came out last July, completely different subjects. And I think that this subject is something where, again, there is more practice than science, but it's an area where we have not learned enough in the past. So I'll try to clarify all this, first of all, going through a few earthquakes in the past, just a few that I know well. There is no specific reason. And just to see that if I could talk about the San Francisco earthquake in 1906 for hours. Many issues came out of that earthquake. The elastic rebound theory came out of that earthquake. So, but in terms of post-emergency management, this earthquake was often reminded as something that should use as a masterpiece because of this building of more than 5,000 small houses in a very short term, and because they were able to recover so many people in a short term, and also because there was the first time in which these houses were rented for a price that was relatively high, $2 per month at that time was a relatively high price. There was a possibility of becoming owner of the house, but not owner of the land, owner of the house. So then, if you want to keep your house, you have to take it and to move it somewhere else, unless you buy the land, and this is another issue. But if you go and read the what happened at that time, you will find that there is also a lot of criticisms. And the criticism derives from the fact that they were using most of the parks in San Francisco to build the houses, and therefore they were depriving the city from one of its main characteristics. And the fact that is indicated as a good point, the fact that in 2-3 years they were able to buy back the small houses is considered to be by someone forced by the fact that there was the Pacific Panama Exposition in 1915, and they needed to take away all these people and all these poor houses to make space for new things and so on. So there were social problems after that earthquake. I will go through very fast through a number of situations just to see that I do not see a trend. We are not improving. We are just jumping from here to there. 2 years after the earthquake in San Francisco, there was the earthquake in Messina. In Messina, it was even a bigger disaster. There were more than 100,000 casualties. The loss of construction was almost total. And what happened is that the Italian government has been funding some of the problems of that time just a couple of years ago. So the problems lasted for 1 century. Again, this earthquake has been something that have been leaving fundamental seeds in the development of earthquake engineering. The first serious code of practice came out in a few months after this earthquake. But if you think in terms of what happens for what concern problem of post-emergency, it was really a disaster after a disaster. And there were discussion again, this part here was in a paper, in a newspaper. And they were discussing, should we build new houses for good, or should we build temporary houses and so on and so forth? And this is more than a century ago. So I'm jumping to 1963. 1963 was the earthquake in Skopje. Again, it's famous for other issues. There has been the first case of isolated building after the earthquake in Skopje in 1963, where the isolation devices have been substituted a few years ago. And what happened here is that they created a number of kind of small cities, small towns around the city as new-founded places. And they created in relatively short terms 14,000 dwellings in 18 new settlements. Here, the criticisms were on the quality of construction, on the fact that they were using prefabrication, which was completely out of the standards of the time in Skopje, the fact that the tradition was completely different, and the lack of public consultation. This comes continuously. People are like to criticize, and sometimes the good part are forgotten and the bad part are remaining. Mexico City in 1985, try to look in the literature, you'll find nothing. You'll find only something that states, but then say, okay, what was the return? What are the number? Nothing is published. But anyway, at least you find papers where the problem is stated. There must be consensus. We should discuss everything with the population, and so on and so forth. In China, in 2008, this is something which is completely out of scale, because there were something like 15 million people homeless. So how can you deal with 15 million people homeless? And again, it's been a gigantic project. They spent $137 million dollars or euros, whatever you want, more or less the same, or pounds if you want. Doesn't make a big difference. But all the indications of what happened in China are coming from official sources from the state. And we are always, I'm not saying that they are lying, but I'm saying that it will be interesting to see something that comes from different voices to understand what really happened. And the criticism there, if you look at outside the official sources, is that somehow they were favoring the wealthier fraction of the population and kicking out of the areas the poorer part of the population. True or not, again, social problems. Well, Japan in 2011 is a very special case because in Japan, the casualties and homeless people were not due to the earthquake in direct form, but they were due to the tsunami of 40 meters approximately and to the meltdown in the Fukushima reactor. But the story is that there was more than 1 million buildings damaged. And they did something, but it is clear. And even if you go today to Japan and talk to people, it's clear that the focus of the government was industry, was to recover from the point of view of the economy of the country. And not everybody knows that after that event in Japan, there were something like 53 nuclear power plants, and 40 of them were stopped. Not for a week, for a significant time, because they wanted to improve the safety of their structures. And finally, I could go ahead for a long time. In Turkey, you remember the 1999, actually 1999 in Turkey, there were 2 earthquakes. There was the Izmit one in August, and there was the one in midway between Ankara and Istanbul in November. But then there had been the one in 2023 in the southern part of Turkey, and for what concerns that the second one in 2023, we do not know yet what will be the outcome. But for sure, there has been significant funding from the World Bank, 1.45 billion euros to help Turkey to recover from that. But what is interesting here is that the post-earthquake, I'm referring now to 1999 earthquake, intervention were not only dealing with residential problems and so on, but also with regeneration projects. So there have been this is the area of a university campus that was completely essentially rebuilt, or actually built after the earthquake. So if we take this as a very short introduction to the entire story, we see that it's difficult to find any line of thought that grows earthquake after earthquake and points in a certain direction. But there are a few things that are clear. When you have a strong earthquake near a major city, about 1/3 of the population normally remains displaced. And 1/3 of a population of a city of, say, 100,000 inhabitants means 30,000 people without a house. Quickness is essential. Consensus is clearly fundamental. Preservation of social identity is fundamental. So you cannot simply say we are giving to the population a place to stay, because this places to stay will remain for years. There has been a lot of discussion, but nothing came out clearly about the fact that it's better to support people or to provide loans with low or no interest. Someone is talking about compulsory insurances to try to have other sources to support. But what is clear to me is the second last point there. We have serious problem to face in emergency only, and this is a subject I will discuss with numbers, when there is a relatively large magnitude event close to a relatively large city. So if this is the case, then you have the problem of considering what to do in a short term and what will happen in the long term. What to do with new settlements, which means, okay, I'm creating new settlements. I will need them for 1 year, 2 years, 3 years, 4 years. In a case I will show briefly in a few minutes, it was 10 years, the time frame you needed those buildings. But a certain time will come when the populations wants to go back to their areas. What are you going to do with those buildings? This is regeneration. You know, structures that are built for homeless people could become student houses, could become places for elderly people, could become, must already have in mind the transformation, must already have in mind what will happen in a time scale that is decades. This is something that is not normally in the interest of politicians. You know that a famous American professor a few years ago came out with a new acronym. Instead of saying NIMBA, you know, not in my backyard, it was coming out with something not in my political term of reference. So everything which is out of my responsibility, I don't care. It's not something that is taking votes to me. Okay, so let's go to a second short part of this presentation, just to introduce an experience I had directly, because I was in charge of the reconstruction after the L'Aquila earthquake in 2009. This earthquake was relatively small magnitude, 6.3 moment magnitude, but the point was that the focus was exactly under a city of about 100,000 inhabitants. So the numbers here are confirmed. We had approximately 70,000 people without a place to stay after the earthquake, and this was reduced later on, but we remain in about half of that, so about 30,000 homeless people. So what are you going to do with when you are to deal with something like that? Of course, you can use hotel, you could use tents, you could in the very short term. Then you should decide which policies you want to follow. And what was done at that time is that the government accepted a proposal to go for real buildings. Real buildings means buildings with a very high level of seismic safety, in which the seismic safety does not mean to prevent collapse, but to guarantee continuity of use, considering that there are going to be for sure aftershocks, and the aftershocks could be at the same level or close, as happened in New Zealand, to the original one. And the second and third points were low environmental impact. So real buildings means low energy dissipation and so on. And then the third point, which was probably the most difficult, to complete the buildings for about 15,000 people in 6 months. So the idea that I developed immediately after the earthquake was that it was necessary to use all sorts of kind of possible materials and construction typology, but working on several tables, it was decided to use, there were 16 different locations to build these new buildings. Nothing had been prepared earlier, so the locations were not necessarily the wisest, but they were locations where in each one of them, something between 2 and 20 buildings were constructed. I will show you what does it mean in shortly. But the point is, if you want to construct what we did at the end is 186 buildings in 6 months, it means that you cannot design a building and say, I will use steel buildings or concrete building. You must use everything you have available. No other possibility. No technology will have the resources to provide you with these figures. The second point is that you needed to have some sort of control of the seismic response, in the sense that you go to the industry and you say, look, I want to have these buildings, but I'll take care directly of the seismic problems. To do that, we decided a system of plates which were isolated. This is 16 years ago. Isolation was not advanced as it is now, and we used more than, okay, now you see the isolation devices that you were seeing is one of these. So these were real tests on 11 of those buildings, and we used more than 7,000 isolation devices, which means that we could tell the industry, look, the building on top is your problem, but design them for 10% of G. Finished. We take care of the fact that it will be not more than that. Actually, it was slightly more, but anyway, 10% of G, okay? So this means that essentially you are not designing for earthquake for the buildings. So you could go fast with what you know. So control of the response means to see what was the demand in terms of displacement. The displacement demand was elastically in between 30 and 40 centimeters and slightly reduced because of energy dissipation. So at the end, we designed isolation devices with a capacity of 260 millimeters displacement. And each one of those buildings, each one of the 186 buildings were built on a plate that was resting on 40 isolation devices with a relatively large radius of curvature and with a relatively low friction coefficient. Actually, again, the friction coefficient was at the end higher than 3%, which was our aim at the beginning. But anyway, of course, we had to rerun all the analysis to see that the buildings were working properly. So this was done how? One of the first point was that for what concerned the lower plate, columns, isolation devices, and second plate, the state acted directly as a general contractor. There was not a construction company. So we were buying concrete, we were buying steel, we were buying isolation devices, we were buying labor. And this saved money for sure, but saved time and increased a lot the quality control. On top of it, it was a standard call for bids for constructors to build the buildings on top of the second plate. Second problem, big problem, was logistics. If you have a place where you have had an earthquake in the center of a country, and you have to move all sorts of goods, material, and men from everywhere else, it's a big problem. It's a big problem. You know, there are regulations. You cannot move things at night. You cannot move them on Saturday and Sunday. You cannot move special trucks and so on and so forth. Big problems. And when you are there, you are in a place where you have problems with the people who are living there, and you are moving there 10,000 workers to construct the houses. And they have to sleep somewhere, and they have to eat something. And this is, again, a problem of logistics that is not easy. I'm saying that because these are the kind of things that should be thought beforehand. All this in the future should be prepared. Should not be left at someone that stays there days and night for a week and invents something, and then if it works, it works. A third point was the production and quality control. I was receiving every day hundreds of pages of reports, well, here you can read, we were able to tell the government how many pages we had been used to do all this job. Not easy, but fundamental. And another level of production and quality control, today this is rather trivial, but 16 years ago was not that trivial to have cameras in all the construction sites in different points, and we managed to put some small solar generator to the cameras and to take photographs, and then to reproduce what was happening and to control what was happening in each one of these 16 places. In each one of them there was a number of houses, and therefore I could every day I could say we have 1 hour delay here or 2 days delays there. The production here was more than 2 million pounds, let's say, per day. So if you have 2 million pounds production per day, then you understand that 1 day is like a month in a standard construction site. So you see here 19 sites. I said 16, but yeah, 3 were added. Anyway, that's not important. And we were able to locate there at the end almost 15,000 inhabitants. But again, here is a big problem because families are not the same. There could be families of 1 person, 2 persons, 3 persons, but even a family of 3 persons could be a young couple with a small child, or it could be 3 elderly sisters that hate each other. And the two apartments that they need are completely different. And you have to match what you are building on one side with the properties of the population on the other side that you do not know exactly. So coming to the engineering part, we were producing the concrete plates faster than the availability of the isolation devices. So we have to locate temporary support, and we must have been able to raise up the plates to take out the support and put in the isolation device. And these were all verifications that had to be done. And of course, we had to do all the detailed design to see how to build the systems. And you can see that's a lower plate. These are columns. This is one of the isolation devices. And you can see that's one of the places. You see 1, 2, 3, 4. Maybe there are 15 buildings there. Each building was 3 stories and about 60 meters by 20 meters. So that's the size of the plate. The building was a little bit smaller, but anyway, you understand that you're dealing with a large number of people. Now, I think that this is a calculation that is rather on the safe side. In Italy, but in most countries, if you have someone who is without a house, it is a cost for the society. He must stay somewhere. You must either use a hotel or a tent or a temporary house, or you is staying with some of his family, some relatives, and normally the Italian government pays something to this person. So if you are able to recover this population faster, you have a direct saving of money. It's a social saving of money. And this is just a direct savings, but you could actually have a much more significant saving if you consider what is the indirect effect. If the people are going back to the region where they were, they will become able to produce. The industry will have the workmanship there. The university will have the families that are sending the students to the university, at least those who are living close by, and so on and so forth. So this was an experience that I think taught us something, but even in my country has not been used as say a starting point to develop something that could be used in the future. Now let me spend a couple of minutes on something which is more theoretical. I've been using this sort of chart in different sorts of presentation recently. In this kind of chart, you have on the vertical axis the annual probability of exceedance. Annual probability of exceedance means that is the reciprocal of the return period. So if up there you read 0.05, it means that 1 over 0.05 is the return period. If you read 0.01, it means the return period is 100 years. Okay? In the horizontal axis, you have the, say, the damage that you are expecting for that level of ground motion. So a point here is what? Point down here is a point where you're completely losing your building, so 100% loss. You have to reconstruct the building, but the annual probability of exceedance could be maybe 500 years, well, 1 over 500 years, 1 over 1,000 years. So this is kind of the point where you are designing for, or where you have assessed the house. You understand? So it's essentially, if you take this point down, you're doing what? You are saying that instead of losing the house for the ground motion that has a probability of occurrence of 1 over 500, you are losing the house for the ground motion that has a probability of occurrence which is 1 over 2,000 years. Okay? So if you're making the building stronger, more capable, you are taking this point and taking it down. The point up there, what is the point up there? The point up there is the opposite, is the point at which you have some starting damage. So it's again somehow conventional. You say that for a ground motion that happens once every 20 years, maybe, you may have a little crack somewhere, nothing else. You don't consider this damage. So it's the level of ground motion for which you have an incipient damage. Now, this curve is governed essentially by what happens in between. The difference between the black or the green or the blue lines, even if they have the same point up there and the same point down there, is that for an earthquake that is inducing a ground motion that has a probability of occurrence, say, of 1 over 100 years, the damage is 10% of the value of the house, 20%, 30%, 50%. So somehow, if you want to have a continued use of a building, you don't need to modify this point or to modify the point up there. What you need to modify is to take down the curve. So if you want to design a hospital that works after an earthquake, you don't care if it collapses for an earthquake which has a 5,000-year return period, 2,000-year return period. You want to have that for that 1,000-year return period, you have continuity of use. If you take this kind of plots and you take the integral under the curve, that integral is by definition the expected annual loss. So it's what you are losing in the average per year. Okay, so essentially what is under the curve is a figure, is 1% of the value, 10% of the value, whatever, 0.1% is the average cost. Of course, average cost means that for 30 years you have 0, 0, 0, 0, 0, 0, then you have 30% because you have had a ground motion there, then you go down and then you have 0, 0, 0, but the average expected loss is there. So that's essentially the value that should be used by insurances to fix what should be the price that you have to pay to be insured. Okay, this is just to try to give us a common way, a common, say, tool to use. Now, if you modify the upper and lower points, you know, the point down here and the point up there, and you see, but is the expected annual loss changing? Very little. The expected annual loss is essentially not a function of those 2 points. Actually, these curves are all curves where those 2 points have been modified, and you see the curve is always the same. So the expected annual loss, which is now in the vertical axis, is essentially always the same if you don't change one governing part of the curve and you make it going down. Good. What does it mean? It means that essentially your losses are governed by the response for relatively frequent earthquake. They are governed by the fact that you can use the building or not after an event. And this is true for the repair cost, but it is even more true if you are considering the so-called indirect costs. For example, if a bridge is not usable and you have, and an important bridge is probably used by 100,000 vehicles per day. And those 100,000 vehicles have to go 50 kilometers away because that bridge is not usable. And you consider what is the social cost of fuel, whatever, for that, you will find out that it's, well, I don't want to enter too much into this, but an important bridge, if it is closed or limited use, is repaying its cost in 3 months. This is the standard value. So it's very relevant to try to avoid the situation where you cannot use the building, or the building or the bridge or the hospital or whatever. And of course, the response of non-structural elements is fundamental. This is also confirmed by this kind of plots. There have been many people working on these issues. Professor Aureli there has been working on this. Eduardo Miranda at Caltech. Many people, not Caltech, at Stanford, have been working on this subject. What can you read down here is that you see return period of the ground motion, and you see the light blue part is the non-structural damage. And the red part is, say, the structural damage, because it's collapse, essentially. You see that only if you go to very rare ground motion, the structure parts come into playing a relevant role. And the two upper plots are telling you that the damage could be produced either by the interstory drift, for example, because doors cannot open, or windows or frames and so on, and by the floor acceleration, because if you have a ceiling like this, the damage of this ceiling depends essentially on the floor acceleration, while the damage to this door depends essentially on the interstory drift. So it means that you have two parameters that you should look at. Good. A few years ago, some of the people working in my group simulated the repetition of the Messina earthquake of 1908, and then came out with a number of victims which was much smaller than the number of more than a century ago. actually maybe 1/4, but with a number of displaced people that was same order of magnitude or even larger, which means that, okay, I'm not happy with 25,000 victims, but there has been some little improvement in under that respect, but there has been no improvement under the point of view of reusing. Now let's come to what to do. First of all, exposure is fundamental. If you have a large earthquake in the desert, you don't have displaced people. So this means that you don't have to consider all possible areas, even in a seismic prone country like Italy or Turkey or Greece or Portugal. This is a map of Portugal. The green area has 33 buildings per kilometers. What could happen there? If you have 10 people without a house, we could solve the problem. We could host in our own houses this kind of people. Now let me give you some figures that I developed specifically for this night. Now I'm looking at the problem of continuity of use, and I say, okay, I take only one of those two parameters. I take the interstory drift, which is more crucial, and I say that if the interstory drift is in the range of say 0.5%, most likely that building could not be used because the doors will not open and so on and so forth. This means that if it is at 0.5% interstory drift, we are far away from yielding. It's probably 1/4, certainly less than 1/2 of yielding, okay? So the response is essentially elastic. If the response of a building is essentially elastic, then it means that its display shape in vertical, looking vertically, is essentially linear, which means that the displacement is the interstory drift multiplied by the height. And then I'm using some equations that are available that are correlating the period of vibration, elastic period of vibration, to the number of stories. What comes out is that I could take the number of story or the height, which is essentially the same thing, calculate for each one of them an approximately correct equivalent period, and then I can calculate the spectral displacement and the spectral acceleration that are connected to that condition, the condition I was saying earlier, okay? And if you do that, you obtain a curve, which is approximately this curve here. This curve here is in terms of spectral acceleration versus spectral displacement. What does it mean? It means that you have a demand, an earthquake demand, a ground motion demand, which is above this curve. Most likely that building could not be used after the earthquake. If you have demand which is below this line, you have some chance. It most likely could be used. So I've created a curve which is essentially expressing the capacity of a normal building to be usable after an earthquake. And this is valid for all sorts of building. And the green area there is where most of the building will be, because those levels of spectral displacement correspond to a certain period of vibration. They correspond to a certain number of stories. So that green area is the area of maybe between, say, 2 and 10 stories, something like that. Okay? Now, if we have this is a capacity, can we compare it with the demand? Yes, we can. And I've been using some of my time in the last years to look into some 8,000 recorded ground motion signals, and to say that, for example, if you have a magnitude 6.5 at 5 kilometers, depending on stiff soil black or medium soil red or soft soil blue or something like that, the demand in terms of spectral demand, spectral acceleration, spectral displacement is shown there. Continued lines, solid lines are average demand, and dotted line are +1 sigma. What does it mean? It means that with today's constructions, if you have an earthquake in the range of 6.5 magnitudes or higher, at a short distance, almost no buildings could be used after an earthquake. Okay? But what happens if I move the earthquake further away? I move it at 25 kilometers. You see now the demand versus the capacity? If the ground motion is originated at 25 or 30 kilometers distance from where you're looking at the building, then almost everything will stay there, will be usable. What does it mean? It means that we have problems if the location of the focus is very close to where you have a dense population, a city or a town. If it's 40 kilometers away, you may have damage, but the number of displaced people will be small. What happens if you take now a close event with lower magnitude? So it's 5.5 magnitude, 5 kilometers. You see, if the magnitude goes beyond, say, 5.5 or 6, again, you have no problems. So we now know the problem. The problem is a relatively large town close to a fault that could induce, say, an event which is larger than 6. And then, of course, you can ask our colleagues, seismologists, to give us a probability of occurrence. But this is reducing our problem. In a country like my country, we do not need to look at everything. You know, the civil protection, if I talk to the civil protection or to the prime minister, he says, we cannot afford to prepare plans for 2,000 places. Don't need to do that. And I'll show you why. Okay, this is just L'Aquila, which confirmed what I was telling you. But in Italy, you could take a number of source zones. For each one of the sources, it is you have associated a certain maximum energy release capacity and therefore a maximum magnitude. And then you can use this to find out something which is similar to a map of seismicity. You cannot have a problem of thousands of people displaced in an area where you can see there a green color or a blue color. Okay, but only in the central part, only where you have a capacity of releasing energy. And if you look at the distribution of population, you see this map, and here are the major cities. The major cities normally, in this case, are not that close to the areas where you can have large earthquakes. And if you put together the two databases, you find out that you do not have more than 50 cases. You can forget all the rest for what concern emergency plans and so on. You should set up reconstruction plans for a very limited number of cases. For those cases, you could do an in-depth study, and you could find out where to build, what are the conditions, so on and so forth, and have your plan in the drawer, so that if you have a ground motion, you know what to do. Okay, if this is the case, then you can, for those places, go and look at the characteristics of the population. And again, be prepared about the fact that you have a certain number of 3 members families or 4 members family and so on and so forth. These are just in the census. And for those areas, you can look at the population distribution. You could look at the additional risk. You could set up the places where you could build new houses. And you could decide the building dimensions, because if it is a flat area, they could be larger. If it is in a slopes, they should be smaller. You could decide the number of stories depending on the construction around and environment and so on. And you could talk about future use and say, look, here I have a university and here I have some space available. I could set up that this area will be the area where I'm going to build in a short term the houses in case of an event. And after 5 years, these houses will become residential houses for students. And of course, you could look at the local soil conditions beforehand. You could look at the elastic spectra, and you could set up beforehand the way of designing this entire intervention. And I developed, and it is in the paper that it's possible to download. There is the description of the process in such a way that I could design these buildings in 1 hour, which means that I've set up the possible kind of isolation devices, the possible level of weight of the superstructures depending on the number of stories and so on. So you enter and you say, I want 6 stories, I want this kind of structures, I want this kind of devices, I want this kind of, and of course you set up kind of a number of columns that you could use, and you pick up that column. You could set up, and everything is there. What has been done in a artistic way after the earthquake in L'Aquila can be prepared beforehand. And of course, you can have for each one of the columns, you can have a bending moment axial force diagram, and you could have different solutions in terms of single or double curvature devices, depending on where you want to have the bending moment due to secondary effects. You have all these choices that are coming into a game that maybe someone today would call artificial intelligence. I'm convinced that artificial intelligence does not exist. Only natural intelligence exists. But this is not the subject of tonight. Maybe we can discuss it later on if you want. And of course, you can develop all the details and so on and so forth. Now, I like to finish this presentation. I'm checking the time, and I'm staying strictly with the time that you gave me. And I say with 2 slides, because I think that this procedure can be applied straightly, immediately. But at the government level, someone asked me, but this cannot be used in lower seismicity zones with high exposure. You know, this is in political terms, this is relevant in the sense that you can lower seismicity. I explained to you that if the seismicity is relatively low, the problem of displaced people does not occur. That cannot be. But if you have a high exposure, means large number of people, means big cities where it could be anyway interesting for the politicians to provide building of new houses that are not used for displaced people, are used for displaced people in the sense that the displaced people is not displaced because of an event like an earthquake, but because there is this need. And well, I took a couple of days and I thought about that, and I said, yes, I think there is a solution to use this kind of approach. Maybe some of many young people here will work on that, and they say, maybe I could do something similar, but not use isolation. Isolation is anyway a cost and is complex and so on. But if I have columns of 600 millimeters diameter, I could have a yield displacement which is not less than 30 millimeters. And with minimal ductility, say 2, which means no damage essentially, between the 2 plates, I mean, where I could have a parking space and so on, no isolation devices. I could have a displacement capacity in the order of 100 millimeters without any problem. And if you do that, and if you are in a lower seismicity zone, you will immediately check out that you cannot have an acceleration which is more than 0.15 G. You know what happens? It happens that you have you remember your yellow demand, actually capacity. If you stay down there, you do not have problem of discontinuity of use. So if I limit the spectral accelerations to 0.2, and I limit the spectral displacement to 0.1 meters, so to 100 millimeters, I am in an area where it is very unlikely there will be any problem of discontinuity of the use of the building. So we should start thinking in these terms. And this, I was talking about residential uses, but think about how many different uses you could start applying these kind of things. And well, you think hospitals. Can I tell you a non-trivial case that will become trivial as soon as I tell you? Prisons. What will happen if you have a prison where you have a large number of people, and that prison could not be used after an earthquake or after an event? It's extremely difficult to treat this problem. And you could think about other cases where this could be used. So I like to finish here with this presentation. Of course, I had to make it very short with respect to what is in the paper, because otherwise could not fit in 50 minutes. I have only 2 more slides. One is that I would like to join Damian in thanking the sponsors for this meeting, because without the sponsors you could not do anything. I hope that the same or other sponsors will be happy to sponsor research projects like the one we were talking about right now here in the UK. Of course, I'm not trying to steal them. And one last slide that I want to show you is that I think that it is appropriate to think about thanking all my former students and people who have been working with me. Damian has been a student of mine 25 years ago. Gerard has been a student of mine. Maybe there is someone else here, I'm not sure. But the Row School that Damian was one of the first 6 students in January 2001, last year at the World Conference in Milan, at the Row School party. And this party was by far the largest number of people that you could even imagine. I normally go to the Berkeley Connection party. This is a small fraction. By the way, Damian is there. This is me. Gerard, I saw him. Gerard, where are you? Somewhere here. No. Anyway, here is Gerard. And so on and so forth. So this is a way of saying, without people, we could do nothing. Without people means with the people you work with, but also with the people that came before you. And we are inventing very little, very small things. Almost everything else comes from ideas that have been embedded by someone who have been coming earlier. And in turns, he was reading something or thinking about someone else and so on and so forth. So I think that this is the most important lesson that I could transmit tonight. And I hope that there will be at the end, after your talk, a small surprise, that since it must be a surprise, I will not say anything about that. So thank you, and I finish here.
So thank you very much. I'm Christian Malaga from Imperial, and it's both a personal and a professional privilege to offer this vote of thanks on behalf of SECET for today's Mallet-Milne Lecture delivered so masterfully by Professor Gian Michele Calvi. As someone that has been fortunate to be shaped by the vision and the academic rigor of the Rosa School, a vision that Professor Calvi brought to life, I found today's event especially meaningful. His reflections on post-earthquake housing, grounded in both technical innovation but also social responsibility, embody the very ethos that he has instilled in generations of earthquake engineers throughout the years. Professor Calvi, your lecture was not only a masterclass in engineering, but also a powerful call to act with purpose and humanity. Your insights into the long-term effects of post-earthquake displacement, the innovative application of isolated houses, the case house, the case study in L'Aquila, and all of the new tools that you have developed based on grounded on fundamental mechanics, but simple to understand to everybody. All that has underscored how performance-based and preemptive thinking and planning can lead to more resilient and dignified recovery for the affected communities. And you have provided a wealth of tools to tackle that problem. So on behalf of all of us here, thank you. Thank you for that leadership. Thank you for your clarity of thought that was very apparent today. Thank you for your firm commitment to advance in our field. And thank you for reminding us that engineering is not only about solving problems, but about shaping the future of communities and people. So please join me all in expressing our appreciation to Michele.
But first, just to explain what's on the screen, if you want to grab your phones at some point, there's a QR code to, I think, for a survey for the ICE about tonight's event. We'll put it up at the end as well. I'm going to start on Michele's surprise while continuing with the rest of this, just in the interest of time, and because the first part you can pay attention to while also paying attention to me. But yeah, thanks again for the great vote of thanks for that, and of course to Professor Calvi. One of the things that we saw from Professor Calvi's last slide was the World Conference in Earthquake Engineering, and I didn't mention amongst his achievements that he was the president or the chair of the World Conference last year. And as part of this, he also had the privilege of writing the official World Conference song. So what you're seeing is a video that was shared at the World Conference last year, including the sort of introductory material. You'll hear the song soon. Hopefully I'll be done talking by then, so I won't have to talk even louder. But yeah, apart from that, just as an introduction to what's going on, once this is finished, we'll all move through into the ready room for the reception. But before then, I wanted to once again thank Professor Calvi. And I kind of had the idea for the gift from our previous chair, who was a Scotsman. So naturally, he bought a bottle of Scotch whiskey for Professor Pecker. New Zealand doesn't have such a strong whiskey tradition, but while I was home in April, I brought back a bottle of New Zealand whiskey, and we have some glasses in here as well, engraved to commemorate tonight's event. So thanks again to Professor Calvi. And yeah, we'll watch the rest of the video, and then I'll invite you all to move through into the ready room. Thank you.
Just celebrated Christmas in 1908, New Year's Eve in the ruins of Messina. I was commuting every day between Tokyo and Kyoto. The Shinkansen was my home, sushi rolls were my food. On the 17th of Jan, I lost my road home. I lost my road home.
I was living in Loma Prieta. San Francisco was too much. When that day at Candlestick, the big game was to begin. Even that was not enough to save lives on Limits Freeway.
We are all fighting, everybody against time. Together, another quake is chasing us. We are all fighting, everybody against time. We don't wanna see again those abandoned in the dust. My home was in Lisbon in 1755. I hadn't been informed, I was inspiring Voltaire.
And I should live in the boat to save my home. I lost my loved home.
We are all fighting, everybody gets time. Together, another quake's chasing us. We are all fighting, together. Another quake's chasing us. We are on fire. Everybody get inside. We don't wanna see again those abandoning the dust. We are on fire. Everybody get inside. Together. Another quake's chasing us.
Andiamo, va, vecchio mio. Siamo forti, eh?
Sì.
Che cazzone,
Facciamo un
che
pezzo.
pezzo che abbiamo fatto,
Abbiamo
ragazzi.
fatto un pezzo incredibile.
Siamo dei numeri uno.
Piano piano mettiamo a posto tutto, vedrai che verrà un bel lavoro. Facciamo entrata anche?
Ok, vai.